Now, in trigonometry, the relationships we have for the sine, cosine, and tangent take on some new relationships as we go through and get a bit more complex. So if we want to go back to use the unit circle to start proving some of these. Now, you remember the unit circle's a circle with a radius of 1 unit, and then we've got a point P, X, Y on the end of the circle on the circumference, and then that will create an angle theta there in a right angle triangle. So this triangle here ends up being a case where we go across X and up Y. So there's where we start to get our three sides of our right angle triangle with an angle theta there in that. So looking at this one here, the sine theta, if we look at sine theta here, would be the opposite on the hypotenuse. So that gives us y on 1 or just y. So we could say that y is equal to sine theta. We're going to use that. Cos theta is equal to, or the adjacent side on the hypotenuse, so x on 1, which is x, so x is equal to cosine of theta. So we start to have that relationship. Now we've seen those relationships before. Now, looking at tan of theta, we can start to say, well, that's the opposite on the adjacent, so we can write that as y over x. Or we can start to say, well, tan theta is then going to be sine theta over cos theta. So there's a relationship we start to get. Tan theta is the same as sine on cos. And the same with cotangent theta, that could be written as the adjacent side, the adjacent side over the opposite side, which could be written as cosine theta on tan of sine of theta. So there's our first two relationships. Tan of theta is sine on cos, and cot of theta is cos on sine. So we have to remember those and be able to use those. Now, if we look at our triangle and we apply Pythagoras' theorem, well, we get x squared plus y squared is equal to 1. But we said cos theta was equal to x, so that allows us to write cos squared theta there, and y is sine, so we can put in sine for y. So we start to get this relationship that cos squared theta plus sine squared theta is equal to 1. More commonly, you'll see it written as sine squared theta plus cos squared theta equals 1. Doesn't really matter which way. So there's some relationships. There's another relationship that we get and we'll use as we go through. Sine squared of an angle plus cos squared of that same angle will always equal 1. And try that. Try it on your calculator. Throw numbers into the same number in for both of those. It will work. Now, how do we get some more relationships? Well, if we start to divide every term here by cos squared theta, so we get sine squared theta on cos squared theta, and then cos squared theta on cos squared theta, and 1 on cos squared theta. That starts to be sine on cos. We said so in the last part that equals tan. So that gives us tan squared theta. Cos on cos squared 1 divided by cos squared, well, that gives us 1. And 1 on cos is equal to secant squared theta. So there's another relationship that we will see and be able to use. So we're able to do our get another relationship there. So there's one relationship, another relationship. Now, divide this equation here by sine squared theta. So, and we'll see what we get here. So we get sine squared theta and 1 over, cos squared theta over sine squared theta. And that would be equal to 1 over sine squared theta. So sine on sine, well, that gives us 1. Cos on sine, we saw, was equal to cotangent squared theta. And 1 on sine gives us cosecant squared theta. So there's our third relationship that we get from basically Pythagoras' theorem being applied to our triangle and a relationship with theta. We call these a parametric equation. Now, It's not the term we use too much in the extension in the 2-unit course. It's more we use in the extension 1 and 2-unit and extension 2. Now, it's a parametric equation because we're gone from a situation where we had two variables, so x and y, and we've written in terms of one variable, theta. So theta will change as x and y changes. But you can see the equation now is only written in one variable rather than two. And that's what we call a parametric equation. So that's what we're looking at. That's what we call these types of equations when they're written in one. We don't really have to worry too much. You won't see that too often. So the other relationships we want to see is a situation where we've got theta and we've got three sides, our opposite sides x, our adjacent sides y, and our hypotenuse z. And for 90 minus theta, well, the opposite side's y and the adjacent side's x. So for sine of theta, well, we can see that would be equal to x on z. For cosine of theta, y on z. So sine of 90 minus theta would be y on z. And cos of 90 minus theta would be x on z. So what we're trying to show here is that, well, if we look at sine theta and cos of 90 minus theta, they're both equal to x on z. So we start to get the relationship that cos of 90 minus theta is equal to sine of theta. And we compare cos theta, which is y and z, and sine of 90 minus theta, which is y and z. They're both equal to the same thing. And so that would be equal to cos of theta. So sine of 90 minus an angle is equal to cos of that angle, and cos of 90 minus an angle is equal to sine of that angle. What does that mean for us? Well, these are what we call complementary angles. So they're complementary relationships. Now, you've probably done that in the junior school, but it's okay. We're going to see that again a bit more as we go through. But keep that in mind, that you have this relationship when you have 90 minus an angle is equal to, if it's sine, it's equal to cos, and if cos becomes sine of that angle. Now, tan of theta, well, that would be x on y, and 90 minus theta, sine of 90 minus theta, tan of 90 minus theta would be y on x. Even if we start to compare the idea that of cotangent of theta would be x on y. So cotangent of theta would be y on x. Let's get that right. And cotangent of 90 minus theta would be equal to x on y. So what we're starting to see there, again, tangent of x on y and cotangent of 90 minus, so tan of theta and cotangent of 90 minus theta gave us the same thing. So we get a complementary relationship with cotangent and tangent in those ones as well. So there we go. Lots of relationships that exist between different trig values. We're going to be able to use those to prove certain, have certain proofs to be done, simplifying functions. Also later on you could use those to do some differentiation and integration as we go through when we start to do calculus, so they can start to apply to calculus and allow us to solve, especially integration. It allows us to simplify some expressions to be able to integrate a little bit easier. So remember, you need to remember all those. You need to be able to reproduce them, and in our next videos we're going to have a look at using those and having those relationships there to simplify some expressions.